In this videocast, we'll look at polyprotic acids and weak bases. What is meant by polyprotic acid? Well, the prefix poly means many, or more than one anyway, and protic means proton. So a polyprotic acid would mean that there's more than one H and then some anion. So H2A, H3A, even H4A, meaning that there's more than one possible dissociation for this acid. For example, if we took a look at the strong acid, H2SO4, this is a polyprotic acid. It has more than one proton. Its first dissociation happens to be strong, and it would form H plus and HSO4 minus. And then the second dissociation would take the HSO4 minus, and this would be a weak dissociation, so we'd draw two arrows, and then we'd write it as H plus and SO4 minus 2. So you can see that the polyproticness of it means that there's actually two sources of H+, one that is quite significant and the other one that is going to be pretty much insignificant or very, very small, and we'll actually do a calculation to show that in just a little bit. So what is meant by the symbol Ka3 for H3PO4? Well, H3PO4 is a polyprotic acid with 3 protons that can be dissociated. The first dissociation of H3PO4 would make it be weakly dissociating to form H2PO4 and an H+. Then this would be a Ka1 because it's the first dissociation, written as products multiplied together divided by reactants. The second dissociation then would take this H2PO4 and dissociate it weakly further into HPO4 minus 2 now, and another hydrogen ion. And this would be what's called the Ka2 because it would be the second dissociation of it. Then this critter right here would dissociate further, and I'm running out of space, but I'll write it right up here. The PO4 minus 2 would dissociate once again weakly to form H plus, weaker than all the other ones, plus PO4 minus 3. And so you can see that this would also have an equilibrium constant. We'd call it Ka3 because it would be the third equilibrium, or the third dissociation of the original acid, H3PO4. So that's what the 3 means down here, is it's the third dissociation. Let's take a look at this mathematical problem involving a polyprotic acid. The solubility of CO2 in pure water at 25 degrees Celsius in 1 atmosphere is 0.0037 molar. The common practice is assuming that all of the dissolved CO2 in the form of carbonic acid, which is produced by the reaction between CO2 and H2O, and they give us the balanced chemical reaction right there. What is the pH of a 0.0037 molar solution of H2CO3, and what is the carbonates now concentration in the solution? So step number 1 is to do just like a weak acid problem like we did before. Writing this equation, I'm just going to write an ICE or an ice table below it. Here's my equation. Okay. And initially I have I didn't write the equation, my bad. First of all, write the equation H2CO3 reacting with water, HOH, and then we'll put some HCO3 minus over here, and it dissociates and gives away a proton to form H3O plus. Okay, and it wants to know the pH. So the thing that we're going to look for is the H3O plus in this problem. So now write the ice table, ICE. Initially, we're told that we have a 0.0037 molar solution. The water we don't care about because it's pure liquid, not going to be in the equilibrium constant expression. None of this and none of this to start with. Then what will happen is we'll lose X of this, gain X right here, and we end up with X, and 0.0037 minus X in the end. Solving for X now to find the H3O plus, it turns out to be X squared. Remember, these two X's multiplied together in the equilibrium constant, divided by 0.0037 minus X. This is the reactants right here, and remember it's products divided by reactants, is equal to our Ka1 now of HC3O4, which if we look up on table 16.3 on page 692 in your book, is equal to 4.3 times 10 to the negative 7th. And just to show you where that is in the book, I do happen to have a textbook right here. You can look on this page right here, page 692, and you can see here's a table of acid dissociation constants of common polyprotic acids, and here's carbonic right here. Carbonic, you can see its Ka1 is 4.3 times 10 to the negative 7th. These are also listed many times in the back of the textbook in Appendix C. So anyway, solving this now for X, we end up with X, which is equal to the H3O plus ion concentration, equal to 4.0 times 10 to the negative 5th. And remember, what we're going to do is we're going to ignore this X right here, and we're going to say this is small compared to the molarity that we started with. And if we'd find the percent ionization to be less than 5%, we know that it's an okay assumption. Remember, to find percent ionization, just take your value of H3O plus, divide it by your original concentration, 0.0037, and multiply by 100. And if we do that, I can do it on the calculator for you here real quick. Enter exponent to the negative 5th divided by our 0.0037, and then multiply by that by 100%. We end up with a percent ionization of about 1% or so. So we're pretty safe making that approximation. Remember, if it's higher than 5%, it's not good to do that. So that answers the first part of our question, what's the pH? As long as we take the negative logarithm of this concentration right here of H3O plus, and the negative log of 4 times 10 to the negative 5th turns out to be about 4.4. So we have a pH equal to about 4.4 for this. So the second part of our problem asks, what is the carbonate ion concentration up here? CO3 2 minus. Now, if you look in our original equilibrium question, we have H2CO3 and we have HCO3 minus, even though it's kind of smeared all over here. But we don't have any CO3 2 minus in this equation. Where are we going to get that? Well, remember the HCO3 minus can also act slightly acidic, and it will dissociate, again, giving away a hydrogen ion, and become CO3 2 minus in water. And so this is why some people don't like polyprotic acids very much, is since I have the concentration of this HCO3 minus, I can write a second ice table with this dissociating and becoming the CO3 2 minus. So I'm going to do this on a separate piece of paper just so I don't run out of room. And I'll keep this right above us because we're going to need the value, or how much HCO3 I had there, as my beginning amount. But I'm going to write the equation now as HCO3 2 minus, HCO3 minus 1, getting ahead of myself there, reacting with water, and then it will have a weak dissociation, forming some H3O plus, and it will form some CO3 2 minus. And I'll have an initial amount, a change, and an ending amount. Initially, what I'll start with is the amount of HCO3 minus that was produced in this reaction. And remember, this was X in our equation. X is the same as the H3O plus ion concentration, and it's just off the screen here. Remember, X was equal to 4 times 10 to the negative 5th. So sliding this up, I'll start with 4 times 10 to the negative 5th amount of HCO3. Water I can ignore because remember it's a pure liquid and won't be in the equilibrium constant expression. H3O plus, remember I've got a bunch of that from this equation up here already. As a matter of fact, it was the same amount as the HCO3 minus. And so I'm starting with 4 times 10 to the negative 5th already in the solution of H3O plus. CO3 2 minus, there isn't any of that, so I'm starting with 0 of that. In my change, I'm going to use a different variable here. I'm going to say I'm going to lose Y amount. I will gain Y amount on this side, and I will gain Y amount on this side. And so at the end, I'll have 4 times 10 to the negative 5th minus Y, 4 times 10 to the negative 5th plus Y, and I will have Y amount right here. And if I write this into the equilibrium constant expression, products divided by reactants, I can write this as the Ka2 of H2CO3. I can look up the Ka2 on that same table that I had before, and that turns out to be the Ka2 is 5.6 times 10 to the negative 11th. And this is equal to my products, 4 times 10 to the negative 5th plus y times y, which is right here, divided by my reactants, 4 times 10 to the negative 5th minus y. Now I'm going to do some ignoring here, because y is going to be insignificant compared to the 4 times 10 to the negative 5ths. And so I can actually get rid of both of those, which makes this a super easy problem to solve, because now look, this cancels with this, and how much is my y value? Remember, my y value is the carbonate concentration. It turns out to be the same thing as the Ka. And so my concentration of CO3 2- in this solution is 5.6 times 10 to the negative 11th molar. Notice that it's a tiny, tiny amount compared to the concentration that I had up here, of H3O plus, or of HCO3 minus, which tells you that there's not a whole lot of carbonate that comes when you dissolve carbon dioxide in water. It's times 10 to the negative 11th versus what you get of HCO3, which is times 10 to the negative 5th, and also it is the significant source of the pH lowering in the solution as well. Our next area asks us to list 3 common weak bases and classifications of weak bases. If you look on page 469, I'm just going to flip that in front of the camera here for just a little bit, it lists a really nice table of several examples of weak bases. Ammonia, hydroxylamine, methylamine, the hydrosulfide ion, and you can see a couple other ones. The carbonate ion is actually a pretty good base as well. And it lists the conjugate acid, the equilibrium reaction, and then it gives a number of KBs for those as well. So those are some examples of some weak bases. Notice a lot of them turn out to be anions. And the next question leads into what chemical characteristic makes a weak base a weak base. And one thing that all weak bases have to have is that unshared pair of electrons. Because remember, to be a base, it has to be a good acceptor of protons, and protons, remember, are electron deficient, and so they'll be attracted to that unshared pair of electrons. And that's why nitrogen containing things many times are bases, because nitrogen likes to form compounds that has a non-bonded pair of electrons. First weak base question says calculate the concentration of OH- in a 0.15 molar solution of NH3. So this is similar to a weak acid question, except for our weak base now is NH3. The most difficult part of doing weak base problems, I think, is always to write the balanced chemical equation. Always take your base and react it with water. Always take your base and react it with water. For that matter, always take your weak acid and react it with water, but it's even more important with bases, because bases get their protons from water. So the proton will go over here to NH3 to form some NH4 positive 1 and some OH minus. And so even according to the Arrhenius definition, this is a base because it's produced or increased the amount of OH minus in the solution. Write your ice table, and it's going to tell you that you have a 0.15 molar solution. None of this, and none of this to start with, and so you will end up losing X, gaining X over here, and gaining X over here, and it's just like a weak acid problem where it's 0.15 minus X, and then this is X and X right here. And we can write KB is equal to X squared, because it's these two X's multiplied together, divided by 0.15 minus X. And if you look up the KB for ammonia, it is 1.8 times 10 to the negative 5th. So if we're going to solve for the hydroxide ion concentration, which is X right here, we can make a really good assumption just like we did with weak acids. We can say that this X is small, and then we can flip this to the other side and take the square root of it, and it turns out that X in this case turns out to equal the hydroxide ion concentration, which is 1.6 times 10 to the negative 3rd molar. A pH pretty close to a pOH, pretty close to 3, which gives us a pH of about 11 or so if you're doing the math. Next, a weak base question is if you have a solution of sodium hypochlorite in enough water to make a 2-liter solution and it has a pH of 10.5, it asks us to do two things. Write the equilibrium of NaClO acting as a base in water, and secondly, to calculate the number of moles of NaClO that were added to the water. So we're asked to find the number of moles. First of all, NaClO is going to be soluble in water, and it's going to give us 2 ions. It's going to give us Na+, and I shouldn't have drawn a double arrow there. This is an ionic compound, and it's going to be very soluble in water. Remember, all sodium-containing compounds are soluble in water. So you're going to get some Na+ and ClO-. This critter right here has some unshared pairs of electrons that are going to act basic. They're going to act basic. And this is where a lot of bases actually come from, is from salts where the anion is going to be a good acceptor of protons. Remember, ClO, if it were an acid, it'd have an H in front of it, and it'd come from the weak acid, HClO. And remember, what's left over after the acid is released as proton is a weak base, as long as it came from a weak acid. So to write the equation, we'd write ClO- plus some water. And remember, for weak bases, always write them reacting with water. If you're stuck, take your thing and react it with water, because water is going to be your source of your protons, and it's going to make some HClO, which is the conjugate acid of this weak base, and some OH-. So that's how NaClO is going to act as a base in water. Secondly, it says calculate the number of moles of NaClO that were added to the water. To find that, we need to find out how much ClO there was, because if you look at the formula right here, if you find out how much ClO there was, that's how much NaClO there was in terms of moles, because there's one of this entire boxed-in thing right here for the ClOs. So it tells us initially that we had a pH of 10.5. I'm sorry, at equilibrium, and it made 2 liters of solution, which will become important towards the end. So initially, we have X amount of this. I'm going to write an ice table here, because we don't know how much of that we added. Okay, we have, ignoring the water, none of this and none of this to start with. At equilibrium, though, we have a pH equal to 10.5, which means my POH is equal to 3.5. Then I could take my 10 to the x key on the calculator to find out, 10 to the negative 3.5, to find out my OH- ion concentration, which turns out to be 3.16 times 10 to the negative 4th. So I can put that in here as my equilibrium concentration of OH as 3.16 times 10 to the negative 4th. And since there's a 1-to-1 ratio here between the OH and the HClO, 3.16 times 10 to the negative 4th also goes in here. That means I gained that amount of each of those. Okay, 3.16 times 10 to the negative 4th, gained 3.16 times 10 to the negative 4th, and I also lost 3.16 times 10 to the negative 4th ClO. So in the end, I have X minus 3.16 times 10 to the negative 4th. Well, setting this up in the Kb expression, and if I look up Kb of ClO minus, Kb is 3.3 times 10 to the negative 7th. This is equal to my products, which is 3.16 times 10 to the negative 4th. I'll square that because there's 2 of them here, divided by X minus 3.16 times 10 to the negative 4th, this animal right here. Anyway, solving this equation for X, turns out that X is equal to 0.3. 0.3 molar was my initial concentration of ClO. Now, it asked for the number of moles in this, because it said how many moles were added. Moles right up here it asked for. See, moles. Okay, and so you can use the molarity triangle. Molarity equals moles divided by liters, and multiply your molarity times your liters. It's a 2-liter solution. It said that up here there were 2-liter solution. Multiply those together and your number of moles must have been 0.6 moles. That must have been reacted. Lastly, in this video cast, we're going to take a look at a relationship between the Kas and the Kbs. And we learned way back when, a couple of video casts ago, that Ka times Kb was equal to 1 times 10 to the negative 14th for dilute aqueous solutions like we're working with in acids and bases here. Well, if we know the Kb for something like NH4, for NH3, we could find the Ka for NH4 plus. Or conversely, if we know the Ka for something like HF, we could find the Kb for the F minus ion because they're related to each other. And you can use this equation to do the solving by sticking the other one in. So let's do letter A here. It tells us find the Kb for F minus ion if the Ka is equal to 6.8 times 10 to the negative 4th. 6.8 times 10 to the negative 4th. And this times the Kb would be equal to 1 times 10 to the negative 14th. Divide both sides by 6.8 times 10 to the negative 4th, and it ends up that Kb in this case is equal to, I believe it's 1.5 times 10 to the negative 11th for the F minus ion, leading you to believe that this is not a very strong base. It is basic, but it's not very strong because it's times 10 to the negative 11th. You could do the same thing for letter B, but one other relationship that's missing from my handout here, but it's probably in yours, is that there's also a pKa and a pKb relationship that you'll find in your textbook and in some problems. Remember, when we put a p in front of it, it means take the negative logarithm of it. So to find the pKa, you simply take the negative log of whatever the Ka is. To find the pKb, you simply take the negative logarithm of the Kb. And there's a cool equation that comes from both of these two that you can say the pKa plus the pKb is equal to 14, just like we did with the pH and the pOH. These equations become quite useful. So remember, since you can find the Ka from the Kb or vice versa, many times you will be given only one of the constants to solve for the other. As a matter of fact, if you look in a handbook of chemistry and physics, most of the times they'll just give you the pKa, and then they'll assume that you can work backwards to find the Ka and therefore the Kb if you need it for its conjugate base.